Hello guys and welcome back. This series we are writing an operating system from scratch, currently finishing up the BIOS bootloader. In the last episode we've worked on the paging. We started working on virtual memory and we wrote some code to do to create a virtual page map for our kernel. And today we are going to finish that work, creating a memory map for our kernel and trying to decide a few things along the way. So let's get started. But first, there are a few things that we need to discuss. First of all, we are using PML4, which gives us 48 bits of virtual addressing. Now, the question that remains to be addressed is what happens for the other bits that are not these 48 bits. So basically we have our bit 0, bit 1, right, all the way to bit 47, and then we'll have bits 48 all the way to bit 63. Of course, notice that we are indexing from 0, unlike Lua developers. So this is very important. Right, so these bits here are used for the virtual address translation. But what values do these bits take, right? Well, the answer to that is very simple. These bits act sort of like a sign bit, where they copy the value of bit 47. So basically that means that bits 63 to bit 48 will have a value of 1 if bit 47 is set, or 0 otherwise. Right. So that means that with this, if we have bit 47 equals to 1, so if this is bit 47, then all these bits will be 1. So from 48 to 63, and these bits we don't care, right? And if bit 47 is 0, then that means that all these bits will also be 0, and these bits we don't really care, right? With this, we can make a very easy comparison to unsigned integers. So unsigned ints, where you have the sign bit, which is the most significant bit, and then you have 31 bits for the value. That means that we can, for example, or let's just take, instead of ints, let's consider chars or bytes instead of ints. So we have the byte 7, which is the sign byte, and then we have bytes 0 to this is a 0 to byte 6, which are the value bytes. It means that we can encode values from negative 128 to 127. All the negative values will have this sign bit set, and all positive values will have this sign bit unset. So that basically acts like these bits, but here we have multiple sign bits instead of one sign bit. And from here we can, if we consider this addresses as unsigned values, then we can actually draw something like this. So this would be our addresses, or our address space, virtual address space. Here we have our bounds, and we're going to see what those are. But here we'd have something like an address 0, where all the bits are set to 0. So this would be our address, so 0, 0, 0. Right. So this would be our address 0, right? And that means that we have split our address space to two halves, right? So here we have just after address 000, we'd have this address here. Right? And it would go to eventually become this address here. And then we go all the way to this address where, so we know that for the biggest address that we can have in this positive region, all the bits below 47 will be set, right? So we'd have something like 0, 0, so this would be our bit 47. And then we'll have from bit 46 to bit 0, we'd have 1s, right? And that value is 0007 FFF. Right, so this would be the highest value or the lowest given, depending on your perspective. But the biggest value in this positive region would be this, right? And in the negative region, the first address that we have above or below the 0 address would be something like 0x this. There we go. So this would be basically, this is -1. And these addresses will grow down until this last address here where the value would be basically FFF 8 and a bunch of zeros. There you go. And this is basically, so 1s all the way to bit 47. So this is bit 63. And then zeros all the way down to bit 0. There we go. So this would basically give us this address space. And as I said, since we now have 2 distinct halves of the address space, usually this, I guess, top half, the negative half, would be called the higher half. And this lower half is called the lower half. No surprises there. So why are we making this distinction here between the higher and lower halves? The idea is very simple. So since in pretty much every process address space, we are going to map our kernel, or at least some of our kernel, if we have multiple modules, that means that we have a choice that either the kernel goes to the higher half and then the process space goes below that. So this would be process and this would be kernel. Or we can do the opposite, where this would be our process. And this would be our kernel, right? So in this case here, we call this kernel a higher half kernel, and in this case, we call this a lower half kernel. And the idea is, if our process is a 32-bit process, and it can only handle 4 bytes addresses, it's easier to load our process or map our process into the lower half, because if we give it an address like this, something here in the middle, and say, for example, C000, something like this, right? This address can be taken, or this full address can be taken, and since it only takes 4 bytes, since it's a 32-bit process, it will truncate this address here at the 4 bytes. And this address that we have here that remains is still a valid address, because we can extend with zeros and it will still be a valid address. Whereas if we had some address like for example. So basically the same address or the mirror address of this in the negative region. If we truncate this, then with just this address here, we don't know if we need to, if we are in the higher half or the lower half, because if we take this address as 4 bytes and then we cast it to a U64 or an I64 or something, then we are going to extend it with zeros, right? And that means that we are going to lose the fact that we have this these bytes set. That means that we are going to take this address and consider it as a lower half address when it's not. So that makes it pretty much impossible to run 32 bits in processes in a 64-bit address space in the higher half, right? So that's why all the mainstream OSs will actually have a higher half kernel, just so that they can have this possibility to run 32 bits processes while mapping them in the first 4 gigs, because that's what I drew here. This is the first 4 gigabytes of virtual memory. And this process here, as long as it's mapped into this 4 gigabytes of virtual memory, it will work fine, even though it's 32 bits and not 64, right? So that's why we need to make this distinction here. For our kernel, we are going to consider a higher half kernel, of course. And now we need to decide a few things that we need to address. So the first thing we need to consider is we have a number of cores, right? So a number of cores of CPU cores, and we want for each CPU core to have an initial stack so that it can run its process and do its initialization, right? So what we are going to do is we are going to consider from this address up this region here will be the stacks for every core. So we are going to allocate 1 page per core for stack for every core, right? So we'd have number of cores times the page size times page size, and this would be the size of this region here, right? Above that, we are going to map our kernel, right? So this would be kernel that we have already loaded into memory. We just need to map it. Let's start the fire. Let's get cooking. Right, so here if we go back to where we are loading the kernel elf file, we can see that we have left some comments here for things that we need to use, and we said that we'll go back for them, and I think now is a good time to go back here because we are going to need these info here to map our kernel. Basically, this is basically the start and the size for every program, for every segment of our kernel, and we need those to basically be able to map it into virtual memory. Right, so what I will do here is I will have to create, so this definitely would not return a void star anymore. Instead, this would return some sort of structure here that would be called, let's say, yeah, let's call it something like this. And this would have, so let's put everything into this file and we'll move this afterwards. So def struct mapping info, and this would be, so we'd like to have a, right, so I think we are going to be missing something else. Right, so let's do something like this. Kernel info, right? And this kernel info here, this kernel info will have an array of mapping info, right? And we'll call those segment mappings. And I guess we can just define some number here. Segment mapping count, something like this. Of course, just going to define segment mapping count to be 256 here. Of course, this needs to go below that. There we go. There we go. That should be a bit better. Right, so here in this mapping, of course, let me just finish up here. And this will have also a U64 entry point, I think this is what we are missing for now. So let's add that there, and then we'll have in this mapping info. So what do we need? I guess we just need a start and a size for every kernel, for every segment, sorry. Right, so this would be a U64 start. Yeah, something like that. Or no, hold on. This I would like to have a physical address. Which would be our segment or mapping phase address, something like that. And then we'll have a U64, which we'll call just length, I think, would be fine. Right, so with this, we should now have everything we need to go ahead and do this. Oh yeah, actually, would need to add something else here. A U16, a U8, which is segment mappings count. So basically, if we haven't filled this full 256 count here, this count here will let us know when to stop the mapping, right? Okay, so let's see here. I guess we can go all the way here just after the checks, and we can create a kernel info struct. I'll call it kernel info. Right. So here we get the entry point. Do we do something else with the entry point here? No, we're just returning. So I guess we can just remove this and replace this with kernel info dot entry point equals elf header dot entry. There we go. Can just remove that. Right, and now we can actually remove these two, and we can create. Oh, we'll need to create something like. No, we just need to do something like this. Info dot segment mapping count set to 0. Actually, instead of this, I will just go here and initialize this to default initialize it to 0. That would be much better, I think. Right, so here we are looping over our things and allocating the physical address and loading our segment to the address. Right, so here we are going to do something like so kernel info, so segment mappings at kernel info segment mappings count plus dot physical address equals I guess it's just load address and oh yeah, actually there's a slight problem here. And of course load address cannot be cast, so we'll have to force it a bit. Oh yes, and it's a physical address. So we need to basically create a p address struct here to put this into. Right. There we go. And of course we need to do pretty much the same thing here, except that now we are going to increment this, and instead of setting the mapping physical address, we'll set the length, I think we called it. And this length here would just be, I think mem size, yeah. It's a U64, so that's great. And here we can just return kernel info. Okay, and this here would also need to return a kernel info. I can do it. Kernel info struct, and it's gonna tell me that yeah, it's not defined that way. So let's go ahead and change that. There we go. And now it's gonna complain that kernel info is not defined. It's not forward defined. So let's just take these two here, and I'll do the cleanup afterwards. But for now, let's just leave it this. Leave it as at this. And now this here would not be a entry point. This would be a kernel kernel info. Let's call it this way, and this would be our kernel info dot entry point. There we go. Yeah. All right. So this looks okay. This looks pretty okay. So now if we go back here and we try to, think we can just go ahead and do something like this. Oops. No. Kernel segments. Can remove this, and this would be segment mapping count. Just so we know how many segments we've loaded, and this would be. So let's remove this. Do something like. Kernel executable entry point at that, right? So yeah, that should be pretty okay, I think. And I guess we can remove this this code here. So let's compile this and see what we have. Right, so we have this issue here where it's complaining that it's not finding a reference to memset main C136. So let's see. 136 is this. Okay, so I see what we did wrong here. So what I need to do is probably call our own memset. So kernel info 0 and size of kernel info. Right, so let's see. Okay, and that solves it. All right, so let's run this and see. Okay, so something is wrong. Okay, so let me try something. I have a feeling that this structure that we've created here somehow overflowed our overrun our stack. So let's do this again. Okay, yeah, so that was it. The structure was a bit too big given the stack that we've created. Right, so it looks like it did fine. One segment at the correct entry point. So let's get to the virtual mapping now. Oh, right. So let's start off by creating this or creating a function we'll call map kernel space like this. This function will take two things. I think we are going to need, first of all, a page map, and then we are going to need to pass it the kernel info that we just got. So I guess for the page map, so page map kernel space is VM create address space, and I think we don't have to give it any arguments. That's cool. Right. Right. So I'll pass it. I'll pass it as a pointer, as a reference to that, and then I need to pass also the kernel info as a reference. So now we need to make this function. So let's go ahead and create. I think it's doesn't return anything. We called it map kernel space, and of course it takes a not so const. I guess it's const. Yeah, let's not care about that for now. A page map pointer, which is the kernel space, and the kernel info pointer, which is our kernel info. Right, and I'm guessing we are going to need to forward declare this. Yeah, so let's just copy that, go all the way here. There we go. All right, so that should make it whine a bit less. Right, so let's think about what we want to do here. So I guess we are just going to use a map to address, and this one takes a const page map, the virtual address, the physical address, some flags, and a boolean for execution disable. Right. Okay, so it looks fairly straightforward. So let's get to that. Right. So I guess the first thing we'd like to map is our virtual addresses for our cores, CPU cores. So let's do something like mapping core stacks to yeah, so let's just have it like this, and then we'll do this. I guess we are going to need something like this. And here we are going to need to do core stacks address, core stacks address, like this. Of course, this doesn't exist. What am I doing? Yeah, so this doesn't exist, so we'll create it. This would be a U64 core stacks address. Actually, yeah, let's make use of the things that we've created for this. So this would be a virtual address, and this would actually be, so let's create this, and this would be value, I think we've called it. And this would be, so we want to map them to 0, right? But we actually want to map them to 0 minus, so the first one would be at 0 minus 1 page size, right? So this would be 0 minus 1 page, or it's called arc page size. Right, and we just need to convert this. And yeah, so that's the first one. Because this memory here is the higher half, so it grows from the most negative towards 0, right? So this, the first core stack will start at minus arc page size, which is something like 0 FFF. I'm trying to do a hex math. This would be something like this, right? And it grows, oops, and it will grow all the way to 0, right? And then the one above that, the second core stack would go from something like E000 to, so we just copy this. There we go. So we'd have, oops, we'd have something like this going on. Right, so this one is the first, and this we need to do, right, so dot value here, dot value, and this also would go dot value. And the reason why I did it this way is because we still haven't implemented the, or haven't we? Oh, actually, I forgot that we did this. We can actually now print the longer addresses without having to do weird stuff. So let's do it like that. So instead of having to do this, you could just do something like this, right? And actually that makes it fairly easy to just go ahead here and get the correct entry point, because before it was truncated. Right, okay, so now we don't really need to do this anymore, just need to do that. All right, cool. So now that we have this, we are going to need to loop over some I think we are going to need to have this I defined somewhere here. So this u to I, since we are going to reuse it for a few other things. So I is less than, and now we are going to need to decide on the number of cores that we want to map, because we might be able, no, actually we can go ahead and get the actual number of cores that we have on the current machine we are running on. But that means that our bootloader will get quite a bit more complex, which is not really the point for now, at least. Because I guess writing a fully fledged bootloader with all the bells and whistles that it needs is actually an exercise in itself, and that's not what we are trying to do. I'm just trying to write an operating system from scratch using the simplest thing we can do at the simplest choices at every point, right? So let's just do something like max core count. Let's define something like this. And of course, here we are just going to do this. Oops, there we go. Right, and for this, we are going to just map to address. And what does this take? It takes the kernel space. Let's make this const. So it takes kernel. So it takes a page map pointer. It takes the virtual address physical flags. All right. It takes the physical address. So core stack address, and so let me just do something like stack address. Yeah, something like that. Of course. There we go. And of course it takes the physical address, which will be, we haven't decided what physical address we're going to use yet. I guess we can just allocate some, right? So void star core stack equals pm alloc. And here we need to give it a size, so that would be page arc size, and a type, which would be so what are the types that we currently have? Boot info. I guess we could put it under kernel modules. Yeah, for now. Let's so mmap kernel modules. Right, so that's our physical address. So if we just go ahead and do paddr and set the value to core stack. Of course, this would be U64 core stack, and then we are going to need to give it some flags, which would be just like as so I guess we call them default flags. VM default flags, yeah. For now, that looks pretty okay. And of course, we need to give it the execution disable. I guess we are going to set it to true or false. Yeah. Yeah, our false is all caps. Cool. Right, so now let's go ahead and define this max core count somewhere. I guess I'll just go ahead and put it under arc for now. Max core count. And for now, I'll define it to 64. I think 64 cores is more than anyone can ever need for our OS. Right, so that looks good. That looks good. And now I guess it's just complaining that this doesn't have the const qualifier here, so that should be fine. Now it's happy. And of course, once we finish mapping this, right, so we might actually want to do this differently. So this would be a U64 stack thingy, and this would be that minus that, and this would be the address that we create here with a value of core stack address. Right, and that means that we can just go ahead and do core stack address minus equals U64 arc page size. Right. So after we map every core stack, we decrement this address here to map the next one. That looks pretty okay. Right. So now let's, I guess, decide where we want to map our kernel itself. Right. So we can do a few things, right? We can rebase our kernel to be right after the core address stacks, right? And to do that, we are going to, or we could actually go ahead and do some pointer math to move all the addresses that the kernel has given us by some amount. The only problem with that is that we then will have to edit the symbols on the kernel, the external symbols that the kernel will expect, to actually make them point to the correct locations. And I don't think it's something that we want to do. So for now, we'll just map the kernel wherever it's asking us to be mapped. Actually, this needs to be removed. So for now, we are just going to map the kernel where it's asking to be mapped. So let's do printf and do mapping kernel to kernel segment to 0x capital X, and of course this would be I guess this would need to be done inside a for loop. Yeah. So let's do something like this, and here we'll need to do for I 0, I is less than, and here we got past the kernel info, and we know that we have the count on that, so plus plus I, and we can go ahead with this. Of course, this goes up here, and I think we are still missing something here. In the kernel info, we are still missing one important piece of information, which is the total size of the kernel. But I guess we can just find out ourselves, right? So let's do something like U64 kernel size. Right. And here, for every segment that we get, we can do kernel size plus equals the, hold on, let me just define, I guess we call that mapping info, and I guess this would be just a pointer to something, segment info, and this would be so kernel info segment mappings at I. Yeah, looks pretty good. And this would be segment info dot length. There we go. That looks pretty good. And this would be, of course, segment info dot physical address. Yes. Actually, we still have another issue here. We have the physical address of each segment, but we don't have its virtual address, which is something that we actually need to have. So let's go ahead here and see. Actually, we do have the virtual address of the segment, it's just that we haven't used it. So maybe we can make use of it then, and in yeah, let's call this physical address, and let's add a virtual address, something like this. Right. So where are we creating our so this is phase address, which is the load address, and then we'll just yank this and say that virtual address is I guess we can do something like program, yeah, that should be it. Program header dot v address, right? And of course, this would need to be a v address. Cool. And with this, we should be fine. And of course, this here would need to be phase address. And actually, we can do from 0x send x to, and this can be phase address, and this can be actually segment info virtual address. Right. Okay. So with this, we are doing pretty okay. So let's actually go ahead and do the mapping, right? So map to address, and we can put this into so yeah, we need to pass it the kernel space. We need to pass it the I think virtual address first. So segment segment info virt address, and then segment info physical address, and then for the flags, I think we I think for now we are just going to pass it the default flags again. So default flags, and this would be false. And with this, I think we have enough for this to be mapped correctly. Now the only question that remains is actually finally we haven't needed this kernel size. So I think we can just get rid of it for now. I think this mapping will evolve quite a bit once we start working on the kernel. But for now, we are just trying to do the minimum required thing so that our kernel can actually run. So one last thing I want to do here is I want to map the first, I'd say, 16 megabytes. I'd like to map them in an sort of identity mapping, which means that the physical address will be equal to the virtual address, right? Or put maybe we should put it the other way around. The virtual address will be equal to the physical address underneath. So there will be pretty much no actual mapping. It's just that we are going to expose some physical addresses on the top 16 megabytes as virtual addresses or into our virtual address space. So to do that, we are just going to, again, create a for loop. I is less than, I guess we do have this, yes. This is pretty cool. Actually, let's make it 64 megabytes. Let's make it 64 megabytes, why not? So 64 megabytes divided by arc page size, and plus the I, of course. And here we can go ahead and do a map to address our kernel space. And here we need to give it a virtual address, which would be the address, which will be so it'll start at I. Yep. And the physical address will pretty much be the exact same. So it'll start at I. Of course, here the I shouldn't be. No, actually, we can do it this way: arc page size. Or we can avoid doing that and instead do this. Right. And here we avoid doing this. So VM default flags and false. Yeah. There we go. And with this, we should have the first 64 megabytes identity mapped, meaning that if we access address 0, it will, virtual address 0, it will redirect as it will get translated to physical address 0. That means that some of these addresses here that we have might have been remapped here, but that's okay because that's what actually we need, because once we start using virtual addresses, we will have absolutely no way to go back and use physical addresses to access something, meaning that if we want to modify something in our address space, in our page map, unless we have our page map mapped somewhere in the virtual address, there will be pretty much no way to do that. And there's another trick that is used here to do that, where we basically recursively map every entry of the page map. So these entries here, we can recursively map the last entry of every one of those to point to the actual structure itself. So that way we can have addresses that point to the structures, mapping structures themselves. But we are not going to do that for now. Okay, I think with this we should be good to go. So we just need to basically go ahead and check our page map after we create it. All right, so let's run this and see. Here we can see that we have actually mapped our core stacks to one page below 0. And we have mapped our kernel from, so we only have one segment on our kernel with the entry point at this address here. And we can see that we have mapped that address from its physical location to the virtual address that starts at the entry point of our kernel. We have done it yet again. We have finished our paging. The only thing that might change in the paging is mapping the frame buffer if we want our kernel to have early access to the screen and stuff like that. But for now, we are not going to do that. And the good news is that we are almost done with our bootloader. The only thing that remains is to actually switch to long mode, set a few kernel registers, and then jump into our kernel. Well, that's pretty much it. If you've liked this video, hit like and subscribe. Let me know your thoughts in the comments or by tweeting at me, and join the Discord if you have any questions you want help on. Until next time, see ya. Bye.